If you've ever taken calculus before, you're probably familiar with the Fourier series, which takes any periodic function in time and decomposes it into the sum of a constant and then a series of sines and cosines, or sinusoids. Each of these sinusoids are defined by their frequency, and we're summing over each individual frequency of sine and cosine. Let's look at this white noise signal as an example. This signal is represented in what is called the time domain, because each point on its plot represents amplitude as a function of time. This erratic scribble is what your eardrum actually vibrates at when you're listening to white noise, which is pretty unpleasant. But despite it being so messy in the time domain, if we instead decide to translate it to what is called the frequency domain using a Fourier series, we get something really neat, a nice straight line. The line is really straight because each frequency from, say, 20 Hz to 20,000 Hz is equally represented in a white noise signal. This is because a white noise signal is composed of a sum of all the cosines and sines of all different frequencies. In practice, your signal is not going to look this straight. It will probably look more like this for two reasons. Firstly, the white noise signal that you're recording on your sensor is unlikely to be perfectly white. And secondly, the sensor that you're using is not going to be equally sensitive to all frequencies. So we have a periodic signal which we can decompose into sines and cosines of various frequencies. The next question then is, how do we calculate those coefficients at each particular frequency? The answer is to use a Fourier transform. Now, if you're familiar with calculating correlations, the Fourier transform is essentially the same thing. You're multiplying a function, or in our case the signal, by an analyzing function, which in our case are sinusoids. Wherever the function and the analyzing function are similar, they'll multiply and sum to a large coefficient. And wherever the function and analyzing function are dissimilar, they'll multiply and sum to a small coefficient. Now we can represent the sinusoids, the analyzing function, as a complex exponential. But if you're afraid of complex notation, don't be discouraged. This representation actually makes the integral much easier to use, and the result is you get one complex coefficient per frequency. If you insist on working in real notation, you can. However, you'll end up having to calculate two different integrals, one to correlate the signal with a cosine function and one to correlate the signal with a sine function. And the result is you get two real coefficients per frequency. Now, the question is, would you rather work with one complex coefficient or two real coefficients? And most engineers find that working with one complex coefficient and completing just one integral makes things a lot easier. And in the coming slides, you'll find that it's actually not too difficult to work with the complex notation. Something else that may be disconcerting to you about this equation is having to run the integral from negative infinity to infinity. Luckily, you don't ever have to do this in practice because you're always collecting data on a signal within a finite time frame. An analog to digital converter also cannot sample continuously, so what you end up with is a set of discrete points running from time equals 0 to the nth sample that you were able to take. In order to conduct the Fourier transform on a discrete set of samples, we have to use the discrete Fourier transform, which is only slightly different from the continuous Fourier transform which we were describing earlier. Rather than running an integral from negative infinity to infinity, we're instead evaluating a summation from the n equals 0th sample to the n minus 1th sample. We're still looking for frequency coefficients, but rather than being able to evaluate at any frequency we want, we're restricted to a set of frequency bins, which is determined by our sampling frequency and the number of samples that we're looking at. You'll notice also a difference in the exponent, and this is similar to the last point that I just made. Because we can't look at frequency and time, f and t, continuously, we instead look at the kth frequency bin and the little nth sample. So k over large N, which is the total number of samples, corresponds to the frequency f, and little n corresponds to t, or time. Let's focus on expanding the summation for the discrete Fourier transform. In order to simplify things during our expansion, let's call everything after the complex j term b sub n. That way, when we expand the summation, we get a sum of all the samples multiplied by complex exponentials. Now, how do we deal with this complex exponential? We use an identity through Euler's formula, which states that e to the power of jx equals cosine x plus j sine x. That way, when we use this identity, we can expand the entire frequency bin equation into a bunch of sines and cosines. Once we sum everything up, what we end up with is a constant complex number. But how do we use this complex number? Well, you can plot this complex number on a complex plane by using the real and the imaginary parts of the number as coordinates. Once you've plotted the point, you can extract information about this vector's magnitude by using Pythagorean's theorem, and extract information about its phase or its angle by using an arctangent. The magnitude that you end up calculating corresponds to the amplitude of the sinusoid at that frequency bin, and the phase or angle corresponds to how much that sinusoid at that frequency bin is shifted. The best way to understand all of this is to try out an example. Let's look at an incredibly simple sinusoid, a 1 Hz sine wave at amplitude equals 1. Because the Fourier transform decomposes a signal into a set of sinusoids, we expect to see a 1 amplitude value at the 1 Hz frequency bin once we've calculated the Fourier transform. First, let's set some parameters though. The sampling frequency for this example is going to be 8 Hz, and we're going to use 8 samples. So the samples are going to look like this across our sine wave. We can get the values at those particular points, and once we have those values, we have enough information to begin doing our discrete Fourier transform. So let's begin. Looking at the 0th frequency bin, we can see that the k term is equal to 0, and that gets rid of the exponential term, or makes it equal to 1. Thus, the 0th frequency bin is simply the sum of all the samples from x0 to x7, which we can see is 0. So we can move on from that term. The first frequency bin is we can expand out the exponentials and then use Euler's formula to change that into a set of sines and cosines. And we can perform those operations and add it all together. And what we end up with for the first frequency bin is negative 4j. Now, for the second frequency bin, we can do the same thing. Write out the values inside the exponentials, and then replace those exponentials with cosines and sines using Euler's formula, and then perform those operations, and then sum it all together, and you'll find that the second frequency bin is equal to 0. Now, if we calculate the rest of the Fourier coefficients, or frequency bins, we'll find that only the first and the 7th frequency bin have values that aren't equal to 0. We can calculate the magnitudes of those frequency bins and find that they're equal to 4. And then we can plot all the magnitudes of all the frequency bins on a spectrum plot. Now, the frequency resolution of the frequency bins is equal to the sampling frequency divided by the number of samples. In our case, that's 8 divided by 8, so that equals 1 Hz. So each subsequent frequency bin is 1 Hz greater than the previous frequency bin. We can see that we get a value for the first frequency bin, and that makes sense because that corresponds to 1 Hz, and we have a 1 Hz sine wave. But why is there one over at the 7 Hz frequency bin? Well, this is what's called a two-sided frequency plot. And everything above, and it's impossible to measure frequencies above the Nyquist limit, which is the sampling frequency divided by 2. So what you do is you get rid of all the values above the Nyquist limit and simply double the value that you have, every value that you have below the Nyquist limit. So in our case, we get a magnitude of 8. Well, 8 still isn't equal to 1, which is the amplitude that we expect. And that's because we used 8 samples to calculate our Fourier coefficients, so we actually need to average it out over the 8 samples to get our amplitude equal to 1. So divide it by 8, the number of samples. So we have a single-sided Fourier coefficient of 0 minus 8j, and we can plot that on a complex plane. if we measure the angle off of the positive real axis, we get a phase angle of 3 pi over 2. As a result, we have an amplitude equal to 1 and a phase angle of 3 pi over 2. How do we know that's correct? Well, the angle of the phase is based off of a cosine wave. So if we shift over to 3 pi over 2 on the cosine wave, you'll find that actually that's just a sine wave. So that's what we end up with, a sine wave of amplitude equals 1.